Imagine this. You're in your chemistry lab, practical period. You've got your lab coat on. Maybe you're a little worried about the Viva.
Usual scene,
You
yes.
pick up a test tube. It's got a clear liquid, let's say acetone, at room temperature. Then you take another one, chloroform, also at room temperature. You pour them together.
Okay.
Now, you don't use a Bunsen burner, no heater, nothing. You just mix them. And suddenly, when you touch the beaker, it feels warm, genuinely warm.
It's quite a surprising thing for a student to experience, isn't it? You haven't added any heat, but the solution is generating its own. It feels a bit like magic.
Exactly. It feels like, how? How did heat just appear out of nowhere? And that is precisely what we are going to unpack today. Welcome to another deep dive. We're tackling ideal and non-ideal solutions from Unit 1, Solutions.
And this is a truly crucial topic. It's the bridge between the simple theory everyone learns first, like Raoult's law, and the, let's say, the messy reality of how chemicals actually behave.
And looking at our notes, understanding this is really the key. It helps predict why some mixtures behave perfectly. Like model students, you could say.
Yes. While others surprise us with these heat changes or even volume changes, it explains why Raoult's law works for some things but completely fails for others. If you want to master this unit for your boards, you have to get this concept.
Okay, let's start from square one. We keep using this term ideal solution. It sounds so abstract. What does it actually mean in chemistry?
At the simplest level, an ideal solution is a mixture where the components are so similar that they mix without any drama.
No drama, like that.
No heat released, no heat absorbed. It's a completely uneventful mix. Imagine you have two buckets of paint. One is white, and one is maybe a slightly off-white. Chemically, they're almost identical. You mix them.
And they just blend smoothly. The paint doesn't get hot or anything.
Precisely. That's an ideal solution.
Just it's like mixing twins. They're so similar they don't even notice the change.
That's a great way to put it. Let's do an imagine scenario. I want you to just picture two types of molecules. Let's call them type A and type B.
Okay.
In a beaker of pure liquid A, you have A molecules interacting with other A molecules. There's a certain force of attraction there. Same thing for B interacting with B in its own beaker.
Right. A holding hands with A and B with B. They're comfortable with their own kind.
Spot on. Now, in an ideal solution, when you mix them, the new interaction that forms between an A and a B is exactly the same strength as the old AA or BB interactions.
So the system feels no difference at all. It's like, oh, I've just swapped one neighbor for another, but they're identical anyway.
Exactly. The molecules don't really care who they are next to. And because of that, nothing changes energetically.
Which leads to some important conditions, I assume.
Two very important conditions. First, because the forces are identical, there is no enthalpy change on mixing. We write this as delta H mixing equals 0.
Meaning no heat is released or absorbed. The beaker doesn't get hot or cold.
Correct. And second, there is no volume change. Delta V mixing is also 0.
Okay, wait, let's pause there. The volume thing. That sounds obvious, no?
Yeah.
If I mix 50 milliliters of something with 50 millibels of something else, shouldn't I always get 100 millibel? Isn't that just basic maths?
In basic maths, yes. But in chemistry, not always. For an ideal solution, yes, you get exactly 100 millibel. But in the real world, sometimes you get 98 millimels, sometimes 101.
Wow, okay.
That's where it gets interesting. But first, let's get that exam-safe definition down.
Right, the one you can write on the answer sheet. The insert-safe one.
Listen carefully. An ideal solution is a solution in which the solvent and solute interactions are identical to the interactions with impure components, resulting in no enthalpy change on mixing and perfect adherence to Raoult's law.
That's the one. But you know, our source material points out a common confusion. Students hear the word ideal and they think it means perfectly existing, the best kind of solution.
Yes, that is a huge misunderstanding. Ideal doesn't mean it's the best. It's the theoretical model. Most real solutions are actually non-ideal.
So ideal is like the frictionless surface in a physics problem. It's a concept to help us understand the rules.
Exactly. It's our baseline for comparison. Most of what you mix in a lab will be non-ideal to some extent.
Okay, to get a better grip on this, our notes have a great analogy, the balls in a bag comparison.
Ah, yes, a classic. So for an ideal solution, imagine you have a bag of cricket balls and tennis balls. Let's say they're made of the same material, just different sizes. You shake the bag, they mix completely randomly.
They don't stick together or push each other away, just random distribution.
Correct. Now for non-ideal, imagine mixing oil-covered balls with water-loving balls. They won't mix uniformly at all. The water-living balls will clump together, and the oily ones will be pushed aside.
They segregate. They prefer their own kind. That makes a lot of sense.
The notes also have that party groups analogy, which I think is very relatable.
Oh, absolutely. An ideal solution is a party where everyone is friends with everyone equally. No awkwardness.
A very harmonious party, yes. But a non-ideal solution is like a party with cliques. Some people prefer their own group.
That would be a positive deviation where they want to stick together and avoid others.
Correct. Or maybe two different groups are strongly attracted to each other, forming a new tight-knit group. That's negative deviation.
So why did chemists even develop this concept? Why does it exist?
Well, they needed a framework. They needed Raoult's law as a rule book for the simple cases. Once you have the ideal rule, you can start to understand and predict when and how things will break that rule. It lets us predict things like azeotropes.
Azeotropes. Okay, we'll get to that. First, let's run that mental movie from the source notes. I want everyone listening to picture this. Scene 1. The ideal scenario.
Okay. Picture two liquids, hexane and heptane. They're like structural twins, both simple hydrocarbons. You pour them together, and they just blend calmly. No heat, no volume change. A very polite meeting.
Very civilized. Say,
Yeah.
Scene 2. The drama. The non-ideal case. This goes back to our intro example.
Yes. Now picture acetone and chloroform. This is the classic example of negative deviation. Acetone has a polar carbon-oxygen double bond. Chloroform has a particular hydrogen atom when they meet.
They don't just sit next to each other.
No, they form a strong hydrogen bond. They are actively and strongly attracted to each other. They pull each other in for a tight hug, you could say.
And that hug releases energy.
Yes. That's why the mixture gets warm. It's an exothermic process. And here's the really counterintuitive part. Because they're hugging so tightly, they pull closer together. The total volume actually shrinks.
That's amazing. So if I mix 50 milliliters of acetone and 50 milliliters of chloroform, I genuinely get less than 100 milliliters.
You might get something like 98 or 99 milliliters, yes. The mass is conserved, of course, but the molecules have packed themselves in more tightly.
That perfectly sets up our example section. We've talked about the hot beaker and shrinking volume with acetone and chloroform. That's negative deviation, right?
Correct. And a negative deviation means the vapor pressure will be lower than you'd predict. The molecules are holding each other back. They can't escape into the vapor phase as easily.
So what about the opposite, positive deviation, where the molecules kind of dislike each other?
Yes. A great example is ethanol and water. The forces between ethanol and water molecules are weaker than the forces between water molecules or ethanol molecules. They'd rather be with their own kind.
So they try to escape the mixture more easily.
Exactly. And that increases the total vapor pressure above what Raoult's law would predict. And this non-ideality actually creates a massive industrial problem.
The notes mention azeotropic distillation.
Yes. Because ethanol and water form this non-ideal mixture, you cannot separate them completely just by boiling. They form something called an azeotrope at around 95% ethanol.
An azeotrope? That sounds like a sci-fi monster. What is it?
It's basically a mixture that boils at a constant temperature and composition, almost as if it were a pure liquid. So if you boil 95% ethanol solution, the vapor coming off is also 95% ethanol.
So you're stuck. You can't get it any purer by normal distillation.
You are completely stuck at 95%. To get to 99% or 100% pure fuel ethanol, engineers have to use their knowledge of this non-ideality. They add a third component, an entrainer, to break the azeotrope.
So understanding the non-ideal behavior is the only way to solve the practical problem.
Absolutely. If you assumed it was an ideal solution, your factory design would fail.
The notes also have a counterintuitive example. Students might think, okay, most solutions aren't perfectly ideal, but they should follow Raoult's law, roughly. No.
That's a very common but dangerous assumption. Some deviations are huge. Just look at oil and water. The non-ideality is so extreme that they become immiscible. They just separate.
So that's just an extreme case of positive deviation.
You can think of it that way, yes. The water molecules are so strongly attracted to each other through hydrogen bonds that they effectively squeeze the oil molecules out entirely.
It's like a clique at a party that's so tight, they literally push everyone else out of the room.
That is a very accurate analogy for immiscibility.
All right, this is the point where we need to get very clear for the exams. Let's go through the exam-safe clarity lines, the gold nuggets.
Right. If you're taking notes, this is the time. Let's nail these down. There are 5 key points.
Point number 1.
Point 1. Ideal solutions obey Raoult's law perfectly, and you must tie this back to the conditions. Delta H mixing is 0, and delta V mixing is 0.
Got it. Ideal means zero change. Point 2.
Point 2. Real solutions deviate. Simple as that. And why? Because the AB interactions are different from the A or BB interactions. The forces change, so the behavior must change.
Makes sense. Okay, point 3. Let's be specific about positive deviation.
Point 3, positive deviation. Here, the new AB interactions are weaker. The molecules don't like each other much. They want to escape. So the vapor pressure is higher than predicted. And an important detail. The process is endothermic. The solution feels cool as it absorbs heat to mix.
Weaker interaction, higher pressure, cooling effect. Got it. Point 4. Negative deviation.
Point 4, negative deviation. Our acetone chloroform example. The AB interactions are stronger. They're holding on tight, so the vapor pressure is lower than predicted, and the solution feels warm. It's exothermic.
Stronger interaction, lower pressure, warming effect. Perfect. And the last point.
Point 5, azeotropes.
Hmm.
So important. Remember, these constant boiling mixtures only form in non-ideal solutions. If a question mentions an azeotrope, you know for a fact the solution is not ideal.
Brilliant. That is a fantastic checklist. Let's do a quick final summary to bring it all home.
Okay, let's do it. So the core idea. Ideal solutions are perfect mixers. All forces are equal. AB is the same as AA. No heat, no volume change.
And non-ideal solutions have preferences. They either like each other more or they like each other less.
Exactly. For the visual, remember hexane and heptane as the calm ideal twins, and then remember acetone and chloroform as the dramatic heat-releasing volume-shrinking pair. That's your negative deviation.
And for the real-world application, remember azeotropes, like that stubborn 95% ethanol. That's the proof in the pudding that a solution is non-ideal.
And for your exam revision, just watch out for those keywords. If it says heat was evolved or the volume decreased, you know you're dealing with non-ideality, specifically negative deviation.
This has been a great dive. Before we go, here is a final thought for you to think about. We mentioned oil and water separating. Is it just that they don't like each other? Or is it maybe an extreme case of positive deviation, where the water molecules like themselves so much, their own hydrogen bonds are so strong, that they actively squeeze the oil out?
It's a great question. It's not always about repulsion. Sometimes it's about an incredibly strong self-attraction in one of the components. Next time you mix anything, just try to visualize those molecules. Are they forming new strong bonds, or are they trying to get away from each other?
Thanks so much for listening. Keep learning and stay curious.
Good luck with your studies. We'll see you in the next one.